Welcome to the 6th lecture on mass transfer operation 1. In this module, we are discussing diffusion mass transfer. Before going to this lecture, let us have small recap on our previous lecture. In our previous lecture, we have started discussion on steady state molecular diffusion in fluid under stagnant and laminar flow conditions, and we have considered steady state molecular diffusion through variable area. Under the variable area, we have considered two specific cases. One is steady state diffusion through non-diffusing V, and the another case we have considered steady state equimolar counter diffusion. In this lecture, we will discuss on the diffusion coefficient measurements. So, there are two different kind of diffusion coefficient, one is for the gas phase, another is for the liquid phase. So, we will discuss over here the gas phase diffusion coefficient measurements. The proportionality factor of Fick's law is called diffusivity or diffusion coefficient, which we have discussed before while discussing the Fick's first law. Then we can write diffusivity is equal to flux by concentration gradient. So, if we just incorporate the unit of flux and the concentration gradient, we will get unit of diffusivity, which is meter square per second. Diffusivity, as we know, is a function of temperature, pressure and nature of the component and the concentration of other constituents. So, diffusivity of gases decreases with increase in pressure. As we increase the pressure, the diffusivity decreases. So, the relations between the diffusivity and the pressure is inversely proportional. So, DAB is proportional to 1 by P for moderate ranges of pressure, that is up to 25 bar. This is due to the fact that the number of collisions between species is less at lower pressure. Diffusivity is hardly dependent on pressure in case of liquid. So, if we take liquid and if we apply pressure, the diffusion coefficient remains independent. So, it does not change much appreciably. So, we consider the diffusivity is independent on pressure in case of the liquid. The diffusivity and the temperature relation, the diffusivity increases with increase in temperature, and that is directly proportional with the temperature, and it is DAB is proportional to T to the power 1.5. This is because of the fact that the random thermal movement of the molecules increases with increasing temperature. The diffusivity is generally higher for the gaseous components. That is, for gaseous component, the diffusivity is in the range of 0.5 into 10 to the power minus 5 to 1.0 into 10 to the power minus 5 meter square per second, and which is much higher than the diffusivity of the liquids, and the diffusivity of the liquids is in the range of 10 to the power minus 10 to 10 to the power minus 9 meter square per second. The diffusivity value of the gases into solids are in the range of 10 to the power minus 13 to 10 to the power minus 10 meter square per second, and the diffusivity of permanent gases is in the order of 10 to the power minus 10 meter square per second for the polymers. So, this gives a picture on the diffusion coefficient for different situations. There are several methods of experimental determination of gas phase diffusion coefficient. One of them is the twin bulb method, and the other method is very well known method is Stephan tube method. This both the methods generally we practiced in our undergraduate lab. Let us consider twin bulb method. So, basically we have two bulbs which are connected by a narrow or capillary tube. This is the capillary tube, you can see over here capillary tube, and these are connected with two bulbs. All the valves you can see there are three valves, that is VA1 which is over here, VA1, then VA2 and VAT. VAT is connect in middle of the tube which is connected the two bulbs. All are initially kept closed. Now, VA1 is open and then bulb 1 is filled with pure A at a total pressure of PT. So, the pressure for bulb 1 is maintained at PT total pressure, and that is when the other two valves, that is VAT and VA2 are closed. So, VA1 is open and it is filled with a component A, pure component A to the bulb 1. The samples from the individual chambers are then collected and analyzed their composition. The valve VA2 is opened and then bulb 2 is filled with pure B at the same pressure PT. So, this is the similar phenomena, similar process is followed as in case of bulb 1. So, bulb 2 is again filled and with pure B, and then the valve is closed and all the compositions are measured. Now, the valve VAT is opened and diffusion proceed for some period of time, say at time t. Then the valve is closed. The sample from the individual chambers are then collected and analyzed their composition. So, the assumptions over here we have taken that negligible capillary volume, that is the volume of the tube connected the two bulb, are very less compared to the volume of each bulb. The second assumption is each bulb is always of a uniform concentration, and third assumption is that pseudo steady state diffusion through the capillary. What is pseudo steady state diffusion? The pseudo steady state approximation is that at any instant the diffusion through the connecting tube occurs at steady state. So, if we look into the overall process and the time of diffusion, the concentration will slowly change as the time passed, but at any instant the diffusion through the connecting tube should occur at steady state. That means, at any instant the concentration will be uniform in each case. As the concentration in the bulb change a little, a new steady state of diffusion is attained simultaneously. These assumptions would be valid or correct if the time scale for change of concentration in the bulb is considerably larger than the time scale for attainment of the steady state of diffusion through the connecting tube. So, now let us consider Ax is the inner cross sectional area of this tube. So, tube has the inner cross sectional area Ax, and the length of the tube, capillary tube, is L, which is given over here. Then volume of two bulbs, the left bulb is V1 and right bulb is V2. PA1 and PA2 are the partial pressures of component A in bulb 1 and bulb 2 respectively. That means, the partial pressure of component A in the bulb 1 is PA1, which is higher than the partial pressure of component A in bulb 2. So, the diffusion will occur for component A from bulb 1 to bulb 2. If the total pressure in the bulbs remains constant and equal, equimolar counter diffusion will occur. At steady state, the transport of A from bulb 1 to bulb 2 can be written as follows. Ax is the area, cross sectional area of the tube into flux, molar flux of component A, Na, would be equal to Ax dAb Pa1 minus Pa2 divided by RT into L, which is equal to minus Ax into Nb. Since this is equimolar counter diffusion, the Na would be equal to minus Nb, because the component of B is diffusing to the opposite direction. If the partial pressure of A in bulb 1 and partial pressure of A in bulb 2 at any time, for ideal gases we can write minus V1 by RT into dPA1 by dt would be equal to Ax into Na. Let us call this equation A. Similarly, for bulb 2 we can write V2, that is the volume of bulb 2, divided by RT into dPA2 by dt, which would be equal to Ax Na. So, now from these two equations we can write minus d Pa1 minus Pa2 divided by dt would be equal to Ax Na RT into 1 by V1 plus 1 by V2. So, from these equations if we rearrange, it would be equal to minus d Pa1 minus Pa2 divided by dt would be equal to Ax dAb Pa1 minus Pa2 by L into 1 by V1 plus 1 by V2. Let us call this equation C. The negative sign over here is incorporated because the Pa1, that is partial pressure of component 1, decreases with time, while Pa2 increases with time, and hence there is this negative sign in this equation. Now, use the following conditions, that is at t is equal to 0, Pa1 minus Pa2 would be Pt minus 0, which is equal to Pt when time is 0. The second boundary condition is that when t is equal to t, Pa1 minus Pa2 would be equal to Pa1 at t minus Pa2 at t. Now, equation C, which is over here, written over here, is minus d Pa1 minus Pa2 by dt is equal to Ax dAb Pa1 minus Pa2 by L into 1 by V1 plus 1 by V2. We will obtain after the integration is ln Pt by Pa1 t minus Pa2 t would be equal to Ax dAb by L into 1 by V1 plus 1 by Vt into t. The parameters to be measured from the experiments from here is initial pressure in the vessels, which is required. Then we need to measure the partial pressure of one of the component in the vessel at the end of the experiments, the time of experiments to be recorded, and then the mutual diffusion coefficient can be calculated directly from the equation C. Because the cross sectional area is known to us, diffusion coefficient if we wanted to calculate, we need to know the partial pressure of any one component at the end of the operations, and the volume for both the bulbs, the volumes are known and the length of the tube are known, and the time of operation if we can note, then we can calculate from this equation. Now, let us consider an example. To measure the diffusivity of component A, that is carbon dioxide, by two bulb method, the pure carbon dioxide and pure nitrogen is filled in bulb 1 and bulb 2 respectively. The volume of bulb 1 is 4 liters and bulb 2 is 3 liters. These two bulbs are connected by a capillary tube of 5 centimeter length and 2 centimeter internal diameter. The partial pressure of carbon dioxide is given in case of bulb 1 and bulb 2 are 60 kilopascal and 40 kilopascal respectively at the end of 6 hours. So, time of operation over here is 6 hours. The bulb are maintained at 100 kilopascal total pressure and 313 Kelvin temperature. Now, calculate the diffusivity of carbon dioxide. So, the parameters which are given, we know the fundamental equations to calculate the mutual diffusion coefficients, that is ln Pt by Pa1 t minus Pa2 t would be equal to Ax dAb by L into 1 by V1 plus 1 by V2 into t. So, we can rearrange this relation as dAb would be equal to L into V1 V2 divided by Ax t V2 plus V1 into ln Pt by Pa1 at t minus Pa2 at t. The given data, the length is 5 centimeter, which is equal to 0.05 meter. V1 is also given, that is 4 liter, that is we can just convert it unit to the meter cube, SI unit 0.004 meter cube. The volume of bulb 2, that is V2 is 3 liter, which is equal to 0.003 meter cube. Cross sectional area of the tube is given as pi d square by 4. Here d is 2 centimeter internal diameter is given. So, pi into 2 into 10 to the power minus 2 meter whole square divided by 4, which is equal to 3.14 into 10 to the power minus 4 meter square. The total pressure is given 100 kilopascal and the partial pressure of two bulbs are given at the end of the operation. Partial pressure of bulb 1 for component A is 60 kilopascal Pa1 and partial pressure of component A in bulb 2 is 40 kilopascal. Total time of operation is 6 hours. We can convert this 360 into 60 seconds. So, total 21,600 seconds. Now, if we just substitute all these parameters into the equations which we have derived, dAb would be equal to 0.05 into 0.004 meter cube into 0.003 meter cube divided by 3.14 into 10 to the power minus 4 meter square into 21,600 second multiplied by 0.003 meter cube plus 0.004 meter cube ln total pressure is 100 kilopascal divided by 60 kilopascal minus 40 kilopascal. So, if we just calculate, it would be equal to 2 into 10 to the power minus 5 meter square per second. Now, let us consider the other method, which is Stephan tube method. The Stephan tube is consist of a vertical narrow glass, you can see the vertical narrow glass over here, which is joined to a horizontal larger diameter tube to form a T. So, you can see over here it looks like a T and then the vertical tube held at a constant temperature water bath. So, to maintain the temperature of this the liquid which will be poured inside this tube, the bottom tube, and that should be held in a water bath to measure the diffusion coefficient at a particular temperature. Component B, say air is pumped through the horizontal tube which is flowing, that is gas B is flowing over here through this horizontal tube. The volatile component A is taken in the narrow vertical tube. So, the vertical tube is filled with volatile component, so that it diffuses, it vaporizes at a certain temperature or not very high temperature, at a certain low temperature, and then it diffuses through the connecting tube T. Evaporated A diffuses through B and reaches to the top of the vertical tube, then swept away by the flowing B. So, the gas which will diffuse to the horizontal tube, it will be swept away by the component B. Component B is assumed to be insoluble in A and hence considered to be non-diffusing B. The liquid level in the vertical tube will drop very slowly and pseudo steady state condition can be assumed. Let at any time t, the partial pressure of component A at the h distance from the top of the vertical tube is PA1. So, the partial pressure at the top of the tube over here is PA1 and that at the top it is at PA2. So, the partial pressure at this location is PA2 and the diffusion flux of A through non-diffusing B, we can write the equations Na would be equal to DAB PT divided by RT into H PA1 minus PA2 divided by PBLM. Let us call this equation A. Now, PBLM, as we have already discussed before, that PBLM is the log mean partial pressure difference of component B, which is PB2 minus PB1 divided by ln PB2 by PB1, which we can write PA1 minus PA2 divided by ln PT minus PA2 divided by PT minus PA1. Now, assuming a cross sectional area of 1 meter square, the level drops dH meter in dt second. So, the level which will drop at a time of dt is differential area which is shown over here is dH. We can then calculate rho A into dH into 1 divided by Ma, where rho A is the density of the component A and Ma is the molecular weight of component A. This would be equal to the kilomole of A that has been left and diffused. We can then write flux into area would be equal to kilomole of A transferred per unit time. So, Na into area is 1 meter square would be equal to the kilomole transferred rho A dH into 1 divided by Ma divided by time is dt. So, this is equation B. Now, the boundary conditions over here is at t is equal to 0, H is equal to H naught, at t is equal to Tf, H would be equal to Hf. So, using this boundary condition, if we integrate, so using this boundary condition and substituting the equation A in equation B and integrating with above boundary conditions, we can get rho A by Ma integral H naught to Hf H dH is equal to dAB PT into PA1 minus PA2 divided by RT PBLM into integral 0 to Tf dt. So, from this we can get the final equations for after the integration. Tf would be equal to rho A Hf square minus H naught square into RT PBLM divided by 2 Ma DAB PT into Pa1 minus Pa2. So, from this we can rearrange this equation, we can write in terms of DAB would be equal to RT PBLM HF square minus H naught square divided by 2 PT MA into partial pressure difference Pa1 minus Pa2 into TF. So, the partial pressure of A at liquid surface is Pa1, which is equal to the vapor pressure at the same temperature, and the partial pressure of A at the top of the vertical tube, that is Pa2 over here, it would be equal to 0. This is because of the fact that the gas B, which is non-diffusing, is flowing with a high velocity and swept away all the components of A diffusing to the tube. So, the partial pressure of component A at point 2 or at the top would be equal to 0. Now, let us take an example. To measure the diffusivity of water vapor by Stephan tube method, the water is filled in the vertical narrow glass tube and held at a constant temperature of 30 degrees centigrade. The air is flowing through the vertical tube at a total pressure of 1 atmosphere and the temperature is 30 degrees centigrade. Initially, the water level was at a distance of 1 centimeter from the top of the vertical tube, and after 30 minutes the level drops to 1.2 centimeter from top. The vapor pressure of water at 30 degree centigrade is 4.5 kilopascal. Calculate the diffusivity of water vapor. So, we know that DAB, the diffusivity of component A in B, would be equal to RT PBLM HF square minus H naught square divided by 2 PT MA into Pa1 minus Pa2 into TF. The data which are given, that is R is known to us, R 8314 meter cube Pascal per kilomole Kelvin. T is 30 degree centigrade, which is 273 plus 30 would be 303 Kelvin. Total pressure is 1 atmosphere, which is equal to 101.3 into 10 to the power 3 Pascal. Partial pressure of component A at 1, that is Pa1 at the surface, which is 4.5 kilopascal, would be equal to 4.5 into 10 to the power 3 Pascal, and partial pressure of A at 2, that is at the top, would be equal to 0. Molecular weight of water is 18, and then the height is equal to 1 centimeter from the top, that is 0.01 meter. And then HF, the final height after the diffusion takes place, is 1.2 centimeter, which is 0.012 meter. Time of diffusion TF, that is 30 minute, which is equal to 30 into 60, 1800 seconds. So, the PB1, we can calculate PB1 would be equal to PT minus PA1, which is equal to 101.3 minus 4.5 into 10 to the power 3, which is equal to 96.8 into 10 to the power 3 Pascal. Now, PB2 in a similar way we can calculate PT minus PA2 would be equal to 101.3 minus 0, because PA2 is 0, into 10 to the power 3 would be equal to 101.3 into 10 to the power 3 Pascal. So, all the parameters we have calculated. Now, we need to calculate PBLM. So, if we substitute PB2 and PB1, then we can get PBLM, which is equal to 10 to the power 5 Pascal. So, we can then calculate the diffusion coefficient of component A, that is water, into non-diffusing B, which is air flowing through the horizontal tube. So, if we just substitute, we will obtain DAB would be equal to 3.4 into 10 to the power 5 meter square per second. So, in this case we should note that there should be a gap between the horizontal tube and the liquid filled on the vertical tube. Otherwise, if the vertical tube is completely filled, then there will be a turbulence at the top surface, and then we cannot consider the case as a diffusion of component A through non-diffusing B. So, thank you very much to hearing this lecture. In the next lecture, we will discuss different methods, analytical or empirical relations to calculate the diffusion coefficient. Thank you.